Let's start Unit 2, Dynamics, or you call it Unit B if you like. It's all about forces. So the one connection that's made from the dynamics is the acceleration. It's this is the main formula. Change color. This one right here, F equals ma. You guys cannot see that, can you? How about now? It's not very great. Hopefully most of this slides aren't black background. So F equals ma, and the force is a vector, and that's because the acceleration is a vector. So force depends on acceleration. If you want to make an object speed up or slow down, you have to apply a force. And that force is an acceleration multiplied by a mass. Okay, and mass is in kilograms. And you know acceleration is in meters per second square. And that kilogram meter per second square unit is a bit of a beast. So they don't write it like that. They give it a special name after the man who pretty much did all this himself, Sir Isaac Newton himself. So forces are in newtons. That's what we say. A force is in newtons. All right. What is dynamics? Dynamics is the study of forces and their effects on objects. A force is a push or a pull. So that's pretty much what you need to know right there. Push or pull. I would like you guys to just close your eyes and think about, like, if you were standing on a ledge, or how about you're at a well and you're trying to get water out of the well, and you had all this water down, far down into the ground, and you lowered a bucket into that water. How would you get that bucket back to you? You would have to pull. What would you have to pull? A rope, right? So that's a pull, and what you call the force, from your body to the rope, that transfer of energy really, is transferred through all the particles in the rope, and you can actually measure that, because what if the rope snapped? What would cause the rope to snap? Yeah, if there's maybe too much force, too much force. Yeah, you cause the rope to snap. Yeah. Well, what would it be? Too much weight, too much tension. Yeah, those are all forces. We're going to be working with tensions. We're going to be working with weights, and those are all classified as forces. Yep. So what we're going to see is that, and if you flip a few pages ahead, there's a catalog that we're going to fill out, a catalog of forces that we have to be aware of in this course. This third bullet, like it's a must. You gotta know that. So just like with velocities and displacements, you always had to indicate how much and which way. Same for a force. Like, am I pushing on this door? Which way? Whatever, right? Yeah, sure. Let's say this way is east. I'm pushing east, right? Is the door going anywhere? Why? I push on the door. What does the door do to me? Pushes back, yeah. Does anybody know what that's called? The push. Me pushing the door pushing back on me. Anybody know what that is? Yeah, it's one of Newton's laws, yeah. Do you know which one? Yeah, it's the third, yeah. So we gotta know there's 3 laws of motion. Yeah, you guys ever heard that phrase? What is it in everyday language? You say, equal and opposite. I don't know. There's a common phrase. Like there's an equal and opposite reaction, right? That's the physics. So we'll get to that. The next bullet, the FBD acronym, standing for free body diagram, this one's huge. The free body diagram. Like, if you can't draw these, they're like a physical depiction of what's happening. If you can't draw them, it's very difficult to solve some of the more advanced problems. So this slide, you know, it's right at the beginning for a reason. These are the major ideas you have to be able to do to have success in this course, especially the free body diagram, especially. So you cannot skimp out on this process. Like, you got to get good at the FBD. It's like putting on the training wheels before you ride the bike. You got to, you know, let the minutes take care of the hours. So here are just a whole bunch of examples of forces. In A, you push down on the ball and the ground pushes back. You can get the ball started by giving it a little push. Like, is the ball moving before you touch it? Probably not. And then you give it a little push and then it gets going, right? So what did it do? Yeah, it accelerated. And what causes that acceleration? The force. And if you apply a large force, you think you would get a large acceleration. Now I want you to think about a cruise ship. Is it easy for a cruise ship to turn and accelerate? Why? It's very heavy, or it has a lot of mass. What about like a mosquito when it lands on your arm and you just go like this? What happens to it? You hit it. What happens if you hit it? Does it explode? Sometimes? You see its guts go flying and all you did is go like that? It doesn't? No, like it splats, right? Sometimes blood squirts out. So it totally depends on the mass. Totally depends on the mass.
I was just thinking when like you hit it like slowly and you know it just gets that
Or like, what about an elephant?
flapping up and down the other side.
Like if I took a baseball bat, and I had this baseball, and I picked up the baseball and I threw it in the air, and I took a big swing and I smashed that baseball. Where's that baseball going if I hit it? Pretty far? Pretty far? Like if I hit it good, would it go very far? But then what if I took that same baseball bat with the same swing and hit an elephant in its butt? Would he go anywhere? Would the elephant go anywhere? He'd probably... What's the difference between the baseball and the elephant? The mass. Okay? So it takes... Like the force, if you increase the force, you're going to increase the acceleration. The only thing that could really affect it is the mass. Okay? And forces, you could look at this, like especially look at D and E. For D, like imagine the ball is already moving to your left. For D, the ball is already moving to the left, and then you push it more left. Yeah, it's going to speed up. But if the ball is moving towards me, so it has motion to the right, the ball has motion to the right, but then I apply the force to the left, it slows down. Why? Because the velocity and the acceleration are in, opposite. So it's the same stuff as last unit. So when you think of the force causes the acceleration. It's basically the same as last unit. The velocity and the acceleration, if they point in different directions, it's a slow down. If they point in the same direction, it's a speed up. Okay? Let's keep going. So the symbol of force is F with the bar on top of it, and the unit is Newton, and the standard unit is kilogram meter per second square. So make sure you're aware of that. And you can see what 1 Newton is worth. Okay, 1 Newton is exactly 1 kilogram meter per second square. What the heck does that even mean? It's the force required to move a 1 kilogram object with this acceleration. That's 1 Newton. All right, and we use the same set of rules for the angles as before. This one here, 30 degrees. This one here would be 30 degrees north of east. Or what's the alternative? The complement would be 60 degrees east of north. And I personally prefer this one because the angle's made with the x-axis. And then if the angle's made with the x-axis, the cosine is always the x component and the sine is always the y component. That's the one I prefer. This one here is called RCS. We talked about it last unit. The rectangular coordinate system. That's how it's done in math. So everyone needs to know this. So let's just make sure everyone's got it. Stick your hand out to the right. That's east at 0. And you go counterclockwise. So up to your head is 90s at north. All the way around to the west is 180. Down south is 270, and then back to 0 or 360 back at east. So here's a question for you. What quadrant is 450 degrees in? Trickery. Did you think or did you try?
I think it is. Because I mean,
So take off a rotation, right? Take off a rotation. What do you get? You get 90? So it's not in any quadrant, is it? Yeah, it's exactly north. So you have to be able to know a little bit of geometry to have success in physics, okay? Okay, what about 150? Where's 150? Quadrant 2? And what would the reference angle with the x-axis be for 150? 30 degrees here, north of west, and then if you wanted the x components, you would just do the hypotenuse times the cos 30, and if you wanted the y component, you'd do the hypotenuse times the sine of 30. So forces, just like displacements and velocities, forces can be broke down into their vector components. So, like, why would that be important? Think about a tug of war on one rope. There's a whole bunch of people on that side, a whole bunch of people on this side, and everybody's pulling. If my group pulls with 100 newtons and that group pulls with 90 newtons, what happens? My group wins. By how much? So which way will we accelerate? Where the net force lies, right? It's like a net, like a bank account. It's a net force. But what if, and I'll just draw this on the whiteboard. What if there was 4 groups all connected to a ring like this? How would you know where this ring goes? All these people here, all these people here, all these people, all pulling. All pulling.
it's gonna stay there.
Well, it depends. You might have Andre the Giant here and like Mighty Mouse here, right? So it depends on the force, right?
Well, yeah, but
If they were all the same forces, it would stay there. Good. We're going to talk about a lot of that. That's called a balanced force. And do balanced forces accelerate? But what about unbalanced forces? Yeah, that's a huge understanding. Unbalanced forces will accelerate. But like for this problem, you would have to break these into their components. Like this. And you would have to compare this x and this x. See how one is to the right, but one is to the one is to the right and one is to the left? They fight each other, right? This one is to the left and this one's to the, they fight each other, right? This one's pulling up, but this one's pulling down. I drew it bad. Okay, so we have to be able to break it down into their components. We'll bring these out in the lab. These are just spring scales. They're used to measure newtons. So like for example this one, look at this picture. You have a spring scale and with the guy's finger around it, and then he hooks a pail on it. So like, if you put that pail on a scale, what would you measure? So that's a common misconception. You're actually measuring its weight. You're not measuring its mass, you're measuring its weight. Because if you took that pail to the moon and put the moon on the scale, would it have the same reading? Because there's different. Put the scale on the moon. Because there's different gravity, which is a different acceleration, yeah. I put a red box around the picture and said FBD, put an arrow to it. That's essentially what a free body diagram is. The free body diagram is not the pail, it's not the finger, it's not the scale, it's just the arrows. Remember we always draw on these vector arrows? The free body diagram here, look at it. It has an arrow pointing up from a dot and an arrow pointing down from the dot. The dot is like the center of mass. You could put that if you wanted. The dot represents the object. What do you notice about those two arrows? They're pretty much the same size, so they have the same magnitude, but they're in opposite directions. So we would say that these two forces are balanced. So is this thing going to accelerate? It will just hover there, right? So how do you measure the weight of this object? Not by measuring the down force, which is due to gravity, but you measure the up force on this spring caused by the equal and opposite Newton third law. And I'll just let that sink in for a sec. You don't actually measure the weight. You measure this elastic force. You measure the elastic force that's equal and opposite to the gravitational force. And you find out that it's 6 newtons. That's interesting. So in physics, you do a lot of trying to observe the world and explain results. And yeah, you have to do some clever things. Like I can't physically measure the gravitational force, so I'll create a situation where the forces are balanced, and then I know that that down force equals that up force. And there you go, I have the weight of the object. And that's how springs work. That's how scales work. There's those old scales, you know, the old scales where you step on and then the spring goes, like the meter goes back and forth till it finds it. It's just a spring. That's all it is. Okay, free body diagrams. We're probably going to just spend today on this. And they're simple drawings. So like if it's a pulley system that we're working with, you don't have to draw all the pulleys. Or if it's like a person on a I can't even think right now. Like a dog race, like the dog tracks, what are those guys called? Dog sled, yeah. You don't have to draw the dog sled, you just draw a dot. Okay, if it's a hockey puck, like sliding on ice, you don't have to draw the hockey puck, just draw a dot. It's a simple sketch. Or a box. Dots or boxes. Oh yeah, in brackets here. Dots or boxes. And then you have to assume all forces are acting at the center of the object, so you think of it as like a center of mass. And then for every force acting on that object, you draw a vector showing the size and direction of the force. I'm just going to put in one word in there. For every external force, put that in there. For every external force, because there are these internal forces that we'll talk about later that don't affect it. And then you have to definitely label each vector. The numbers are not necessarily, but they can be put right on the diagram, and often I will do that. So. And then this last bullet is your tail to tip. Resultant forces. That's an example. Okay. Here, a rocket is sitting on a launch pad. This is no different than, that rocket is no different than this water bottle. Once it sort of settles, is that water bottle going anywhere? Is it accelerating? Therefore, its forces are balanced. Good. So let's do this. Acceleration equals 0. Therefore, forces balanced. So when I go to draw my free body diagram, I just need a dot or a box. I have an up force and I have a down force, and they're the same size. Roughly, because I'm not a perfect sketcher. And I just need to label those forces. Now the down force is caused by planet Earth and this acceleration due to gravity, which in this class is 9.81 meters per second square. And we give this guy the symbol Fg. Force due to gravity. Now the force that balances it has a special name. It's called the normal force. And it's given a capital N. Or some people use the lowercase n, but I always use the capital N. Not sure why. Okay, so we will talk about that normal force soon. The normal force. The rocket fires its engines and flies upwards. Interesting. The rocket was initially at rest, now it's flying up into the sky. And if we were watching a PowerPoint right now, this thing would fly up in the air and make a cool sound. But I'll save you from that. So in this case, acceleration, is it 0? So acceleration not 0, therefore forces are unbalanced. If the forces are unbalanced, it's going to accelerate. The acceleration is not 0. It will accelerate. It will have a change in velocity. A change in velocity will occur. Change in velocity will occur. How can I draw this free body diagram? Is the down arrow bigger than the up arrow, or is the up arrow bigger than the down arrow? Very nice. It's very natural in that sense. You think to yourself, okay, who's winning that battle? The up arrow wins the battle on the down arrow. Now the down arrow should be the same size as it was on the previous slide. I'm not sure if I did that. But it should be. It's the same rocket. It's got the same force due to gravity. It's got the same mass. Now I can't call this the normal force anymore because it's no longer resting on the ground. And we'll talk about why that's the normal force later. But we can call this something else. Like in aerodynamics or whatever at NATE, or if you took this at the university, like they'd probably, or you're watching TV, they'd probably call this, starts with the TH. Yeah, louder. I heard it. Yeah, thrust. They'd probably call this thrust. But for us in this class, like, all you gotta do is call it the force applied. FAP. Force applied. FAP. I don't know what that is, but sure. Just force applied. Okay, it's just a force applied. And that could be anything. That could be me pushing this door. Okay, it could be me hitting a ball, pushing my friend on the swing on the weekend, Friday nights, you know. Now these ones are two-dimensional. If you looked at those last two examples, they were in the same dimension. They were both vertical. So everything was just one-dimensional, and they just sort of, it's like a number line. They work together on the same axis. But the 2D vectors, they're not going to be so nice. So let's take a look at the first one. How do you add vectors? You got to do what? How to add vectors. Yep, and the answer is beautiful, tail to tip. So if you look at the first one, like, can you guys, I don't know if I had a ruler, but I'm pretty sure the F1 and the F2 cancel. Pretty sure. So I'd be like, there's F1, there's F2. Notice how I'm back to where I started? So I think these just cancel because they're about the same size. And that should be horizontal. There's F3. So this is the F3 is the resultant. Because the F1 and the F2 just cancel each other out. Okay, so I want you to imagine a tug of war where there's these arrows are the 3 ropes. The dot in the middle is a ring where all the ropes are attached. F2 and F1, they pull at the same force, very nice. And then F3 is pulling unopposed. Where is this going to go? Yeah, it's just going to go east. Good. F1 and it has no up and down motion. It just no, there's no collision. The whole system just moves east. Resultant. Now this one, there's 2 forces being applied to a center of mass. So you have to just pick one of them up. Pick one of them up. Which one is it going to be? Let's pick up F2. I don't know why you want to do that. You're just... Oh, come on. There it is. Boom. That's F2. Because you have to pick one of them up. Doesn't matter which one. You could use F1 and move it, and you'll get to the same spot. In fact, I'll show that as well because it's a good idea. You could put F1 there if you want. What shape does that make? Yeah, parallelogram. So that's called the parallelogram method. But basically, you just need to pick one of them up and move it. Doesn't matter which one. And then what's the actual thing that's happening to this guy? This. That's the resultant. I don't know if it's exactly north. Like when you guys get these, you'll have angles and you'll have to work them out. So like, think about F2. Which way does F2 pull? Left and up. Which way does F1 pull? Right and up. Just use left, right, and up. So F2 pulls left and up. F1 pulls right and up. So what happens with the 2 ups? Up plus up is more up. But left and right work against each other. They sort of cancel each other out. And that's why the resultant is only going up. The left and rights, they balance. But the ups add on to each other. Okay, let's do this. Draw a free body diagram, and then I'll let you guys try this worksheet. Okay, skydiver jumps out the airplane and accelerates towards the earth. So for number 1, and I want you to get into this habit when you draw your free body diagrams, the first thing I want you to think about is the acceleration 0 or no? It's accelerating, so the acceleration is not 0. Therefore, the forces are unbalanced. That's a C. Okay, and the skydiver is falling Which way? Down. So he's accelerating down. So which arrow's larger? Good. And that's essentially all you need to know at this point. The labels I still have to teach to you. But I think you can get the down one. What's the down one? Down force is called Fg. Good. Now the up force, you could probably get this. What's the force applied by? What's air resistance? Which is another word for... Who said that? Good job. Friction. It's friction. It's friction in the air. Force friction. And I give that just a capital F, lowercase f. Capital F, lowercase f. Force normal? Because I haven't defined the force normal for you, but it's a good question. Why don't we use force normal here? The force normal is for a surface, like the table. Yeah. When we do that catalog of forces, you'll have notes for that. Okay, so I'm going to let you guys try the next three, and then we'll talk about them. So maybe just think about them before drawing. So that way you don't mess up your notes. So grab a partner and just talk about the next three. All right, so number 2. And number 2 is probably the most important thing we talked about today. The fact that it's falling at a constant rate, and therefore the acceleration is 0. And therefore forces are balanced. And if the forces are balanced, the force due to friction has matched the force due to gravity. They are, in other words, equal and opposite. If you're equal and opposite in all vectors, then you will not accelerate. And the question was, how can you still be moving while forces are balanced? And that's because an object in motion will stay in motion. But we will get those laws shortly. Right. If all forces in all dimensions are equal and opposite, you will not accelerate. And your forces are balanced. But you can still be moving. You can still be in motion. So 0 acceleration, force is balanced, but still moving. That's okay, but still in motion. And that's a common misconception, that if there's no force, the thing can't be moving. And I think that's good enough, because we're going to get a lot of practice with this. So let's just do 1 and 2. You still need that slide? 3 is, you could draw it any way you want. But
What do you mean? It's like a projectile. You make that.
let's do 3. I mean, why not? Why not, right? Let's do 3. Okay. So it's just a projectile. Is that what it said? A cannonball. Oh, okay. So let's just draw like an Angry Bird situation. The Angry Bird goes wee. Okay. And then if you were to draw a dot in any one of these spots, at any one of these spots, and I'll just pick one, doesn't matter where, what force is being applied? The only force that you have to worry about in this course is Fg. But you know from your experience that what? What if it's a windy day? Right? Is it going to have this perfect parabola? No. And in fact, if there was like a crosswind, maybe there's like a force of friction like this. But maybe in a different spot the force of friction is different. Maybe over here it's way windier. And then you would have to take the resultant of those two forces and make a combined vector force. And this path might not necessarily be perfect like this. It might be like, oh. Okay, so this situation where it's FG only is ideal. The FG. What if it was in like a tornado or something? Well, think about the winds yesterday. Like, anybody play golf? In golf, when you hit a nice shot and you're so happy with it and it goes up in the air, if there's a serious wind, your shot could be totally ruined by that wind because the ball is quite small. So the smallest of forces will cause it to accelerate. So this is more of a realistic situation for the flight path. But in this course, you'll only have the ideal situation where it's FG only. So in this course, we actually don't even care about air resistance because it's just way too difficult. It's above our level, above our pay grade, yeah. And then the last one, it's really easy. The textbook resting on the desk. I'll use a box this time. Why not? And is the box moving? So then the forces are balanced. Well, then I guess I need to read better. If the number 4, if the textbook's just resting there, obviously it's not going to move. But if somebody came and pushed it, your one friend that always likes to, mess with you, push to the left, where would you put this force? To the left. And we call that one force applied. So which way is that book going to go? To the left. What I don't want you to do is, like, non-examples are always helpful. Don't do this. It's pushed to the left, so draw the arrow like that. You always draw them from the center of the mass and then whichever way they're acting. So don't do this. That's a non-example, okay? So this, would it have an acceleration? Yes. That's another good question. Let's just, before we stop, would this book accelerate? Why? That's all you need to say. Is it balanced? The left force is unbalanced. If the left force is unbalanced, it will accelerate left. Are the up and down forces balanced? So it will not go up or down. What happens when the book slides off the table and is no longer on the table? What happens? I'm going to change color here. Oh my gosh. Okay. The book has slid off the table. What are the forces now? FG is still there. Is their left force still there? Is the person's hand still pushing it? No. The push happened once. It's a single push. So then as it falls off the table, what's the only force acting on it? Force of gravity. And we can ignore air resistance. So then once this thing is going, it's in what we call free fall. But because it was given an initial push, it has an x component, and so it will have this parabolic path. That's the homework. Tomorrow we'll do the catalog of forces. And but you guys can also do the free body diagrams worksheet. That's extra. Okay? So free body diagrams worksheet I love worksheets. You don't love worksheets? Like, if you don't love worksheets, then you probably hate school.
That's why I'm here every Sunday.
For worksheets?
No. For school.
Here for friends? No. Here for sports? No. Here for dance? No.
Education.
Here for worksheets? Oh yeah.
Education.
And then
Success.
the catalog tomorrow. This we'll do tomorrow. We'll do it tomorrow.